Well, let's begin. Good afternoon, everyone, and probably good morning for anybody who's joining us from the West Coast. Welcome to CGRE NGN Professional Development Webinars. We are very pleased to welcome our speaker today, Dr. Babak Enayati, and he will be talking about grid enhancing technology. In today's webinar, Dr. Enayati will discuss grid enhancing technologies under current field demonstrations. Given the increase in renewable energy penetration, the challenges associated with these technologies and open research areas will be discussed. My name is Megha. I am the co-chair for CGRE NGN webinars, and I'll invite my co-chair to introduce himself.
Hello, my name is Andres Lasso. As Micah said, I'm also the co-chair for webinars. Thank you everyone for joining us.
Wonderful. So quick reminders before we begin. We are recording this webinar. Please be mindful that anything said during the webinar will be recorded. By attending this webinar, you are consenting to being recorded here today. The recording and the slides will be provided on the CGRE NGN webinar page. Please note the link address on the screen, but we will also send out this information after the webinar. Quick housekeeping items. Andres, do you want to take a few?
Sure, yeah. So please, for everyone, keep your questions until the end of the presentation. During the Q&A session, you can unmute yourself. I think I'm not sure if we can do that, or otherwise just type them on the chat feature, and we'll go through them after the presentation. We request you to kindly mute yourself during the presentation, and if you experience any technical issues, just use the chat box to ask for help.
Thanks, Andres. So we really appreciate your understanding and support to make this a quality call, as we would invite Babak. I would like to introduce him formally. He is the Director of Engineering at New Leaf Energy, and he's also the Principal Strategic Advisor at Ampasimon. He has had 13 years of experience in the utility industry, holding various grid modernization, engineering, and managerial positions. He is also very, very active at IEEE since 2006. Currently, he's a senior member and serves as the Vice President of Education on the IEEE PES Governing Board. And he's also the current chair for IEEE PES Transmission Subcommittee. He's very involved, I think, right from the inception on IEEE Standard 1547 and also IEEE P2800. So he spans the distribution side as well as the transmission side. And maybe we can have a side conversation about the gray area on the subtransmission voltages between these two standards sometime. All right, Babak is a registered professional engineer in the state of Massachusetts. So welcome, Babak. The floor is yours. Let me make you a host so that you can share your screen.
Sure, thank you, Megha. So are you going to share the slides, or I'm doing that?
Either can work, Babak. You have host rights, so you're welcome to share if you'd like. Is
okay,
that
sure?
Okay?
Absolutely. Just give me 1 second. Okay, can you see the slides now?
We can.
Okay, perfect. All right. Well, thank you, Megha, and thank you, Andres, for the opportunity. And hello, everyone. Babak Enayati with Ampasimon and New Leaf Energy. I think I looked at the list of the participants pretty quickly. I think I've met most of you actually at some IEEE conferences. So great to see that you're attending this presentation. What I'm going to do today is basically just kind of do a quick overview of of the grid enhancing technologies. We're not going to go dive into. We're not going to have like deep dive into like the details of each solution. That requires its own, of course, like dedicated session. But this is more like a general presentation on why do we need to advance our grids and enhance the capabilities of our current system. In addition to, of course, like investing in and piloting new technologies as well. See if we can minimize this. Oh, there we go. Okay. Our future, I apologize, like it's a really wordy slide, but and I'll summarize it. We want to make our transmission network intelligent for many reasons. Number one is to make sure that we can have better visibility over the health of our transmission system, and number two, actually there's a lot of capacity in the system that could be utilized and is not currently being utilized because we are not we have not invested in like technologies that would give us more information and clarity over the existing capacity of our transmission lines and transformers. So in general, our goal is to deliver affordable clean energy to the customers, right? So this is basically most utilities mission. In order to get there, number one, of course, you need to make sure that your current network, the power system, is being maintained. So there are many solutions like online monitoring solutions that can help you better manage the health of your asset, and at the same time you would invest in like some new technologies, new solutions that allows you to basically better utilize the existing capacity of the system. So from this intelligent transmission network concept, I kind of categorize it into three different categories. Number one, I call it like real-time intelligence. This is basically the investment in some solutions that would help utilities have better understanding of our the health of their transmission lines and transformers. By knowing this, you can basically avoid any sort of like catastrophic failures or transformers, or like some unexpected outages, or like lines and transformers failing. The second category is basically, call it new tools like robotics, some AI, like artificial intelligence, machine learning, and so on, and also investing in some solutions that utilize AI techniques to process like images from that are taken from like thousands of images being taken from utility asset. So you see a picture of this Boston Dynamic spot robot, and the concept of robotics, of course, is not limited to this one particular robot, but since this robot was deployed at the utility that I worked for in the past, I left a picture here just kind of as an example, mention this as an example where we are utilizing robotic solutions to monitor the health of our asset. This particular robot was deployed at an HVDC substation in the Northeast in Massachusetts, where the robot would actually walk into some areas, some rooms with the HVDC substation where like a human being cannot walk into because of the health issues and concerns. We could just do the maintenance and inspection of those facilities only in like particular times of the year where the system is down for like inspection and maintenance. So that was the only time that we could walk in, but this robot can do the maintenance anytime. It handles all the EMF noise and has no issues with that. And surprisingly, in one of the incidents, this robot actually found a concern in that room where we couldn't walk in, and the image that was processed after that, we realized that yes, there's an issue starting to be developed, and we took the right actions to actually avoid any the issue being getting worse, basically. So all the images that we take through, like the robots and drones and helicopters, all that can be actually go into like some software where the AI techniques are being utilized to process those thousands of images per day. So that's where the next I would say, the level or next phase of image processing is going. And the third category that I mentioned here is renewable integration. So I talked about, the goals that we have for clean energy, right? And then reaching our 2050 net zero greenhouse gas emission goal requires us to basically invest in some solutions that could help us better manage our transmission network. In the old days, maybe like building new transmission lines was like an easy solution, but right now it's at the bottom of the list. We don't, we need to first utilize the max capacity of our existing network before we even talk about or consider building new transmission lines. So some of the solutions like energy storage in conjunction with like technologies like power flow control could definitely help us better utilize the asset capabilities, and especially in some areas where some of the transmission asset like lines and transformers are experiencing overload for a period of time during the day, when say like high penetration of solar and so on. Energy storage is being considered as one of the good solutions to actually avoid that overload, and put the storage in a charge mode, and then during low generation time, the storage can discharge. So the point I'm trying to make is as we move towards building that intelligent transmission network, we need to invest in many solutions. And the other thing, before I forget, I need to mention is that all of these solutions need to work together. Okay, so this is not going to be like ad hoc solution on just robotics or power flow control or dynamic line rating or dynamic transformer rating. These systems need to be able to work together, because as I said, we're looking for like kind of like integrated solutions. So in the future, I want to see, and we will see, like dynamic line rating solution working in conjunction with like power flow control or energy storage, or like getting some input from maybe like robotics and maybe like online monitoring solutions as well, where when one asset is about to fail, what kind of control actions can we take to actually make sure that if that asset fails, then the system stays robust and reliable. So that's the futuristic vision for like to make sure that all these devices work together. Let's see why this is not moving forward. Oh, there we go. All right, so today's topic, so I picked a few, let's go back here. So for today's presentation, I'm gonna focus on technologies called dynamic line rating. So, the dynamic line rating and dynamic, for now it's just the DLR, dynamic line rating. But again, this dynamic rating concept is applicable to transformers as well. And then also I'll briefly mention some of the tests that we did on or a pilot that we did back in my old utility days on a power flow controller as well. So let's start with what's happening in the US currently. In December of 2021, FERC actually issued an order called FERC Order 881. This order basically, the goal, the target, the scope is like all transmission lines that are impacted by air temperature. All right, so and the challenge that we're facing is to improve the accuracy of transmission line ratings, and also, as you know, see on the screen, increase overall transmission network efficiency as well. The whole point is that you know, currently in our transmission network, especially lines, we are from operations and planning perspective, we've been utilizing static ratings a lot, and I'll explain what that is. Static rating been like, you know, conservative ratings that have been utilized in the past. The goal of the 881 order is to actually move away from static ratings and utilize ambient adjusted ratings. Ambient adjusted ratings actually considers you know, ambient temperature in determining the capacity of the transmission lines. So for those of you who are not familiar with this concept, basically when the temperature is low, the capacity of the line is high, the transmission line. So the temperature goes down, capacity goes up, temperature goes up, capacity goes down. And of course, like there's like wind speed in this equation as well, but this is just ambient adjusted rating, so I'm not going to talk about wind. Well, we'll talk about wind at the dynamic line rating section. So most of the time, you know, utilities have been considering some conservative temperature for their static ratings, right? And say, yep, in the winter time, maybe, you know, of course, like depending on the region, this can vary. Of course, like, you know, temperature in Massachusetts is totally different than that in California. But for like Massachusetts, you would say like 50 degrees Fahrenheit for wintertime, and then 100 degrees for like, say, summertime. And you would just go with that for like more like static seasonal rating. However, you know, if you're stuck with like 50 degrees Fahrenheit, then at the times that the temperature is cooler than or colder than lower than 50, then you know, because that increased capacity on the line is going to be you know, remain as unutilized, and that's basically the capacity that is missing. So that's the capacity that we think, you know, we can be utilized to basically transmit or you know, clean energy to the customers. There are two issues here. Number one, from planning perspective, this whole concept of ambient adjusted rating and dynamic line rating is still a challenge, and these concerns are valid and need to be addressed. Planners are saying, well, we cannot predict the temperature like a year from now, 2 years from now. They do like, you know, short-term and long-term planning for the system. So so we can't really utilize, you know, dynamic line rating and ambient adjusted rating for planning purposes. That's a valid concern. From operations perspective, I do see that, you know, ambient adjusted rating and dynamic line rating is being utilized, and will be utilized even more in the future, and we'll see some examples on that. So with that intro, back to this the FERC order. The order basically is requiring that, you know, we're going to have forecasted hourly ratings for the next 10 days. Let me see if I can actually, there's a laser here, I believe, yes. So forecasted, we can have like hourly ratings for the next 10 days. And then all these ratings need to be updated every hour. Some utilities have done, and they do have like ambient adjusted rating tables they've been using in the past. They're not being updated as far as I know, you know, on an hourly basis. So that's basically what FERC Order 881 is actually adding to the old practices that some utilities had in the past. The accounts for like some day versus night solar radiation, some emergency ratings also are being considered in the order as well. The order basically for mandated ISOs to work with the utilities to comply with what's in this order, to make sure that ambient adjusted rating is fully adopted by July of 2025. From implementation perspective, how do we basically implement this? How are we gonna, what phases do we need to look into to implement what's being asked in the order? Number one, you would go with like some identify ambient adjusted rating lines and some candidate rating points. The reason that I mentioned this is like, you may be concerned on, some of the ratings that some lines that are about to be overloaded under like some contingencies, whatever your planning practice or operational practices are. So once that happens, then you'll say like, yep, these are the lines that I'm very concerned about. The actual loading on that line is pretty close to the static. So you basically prioritize those lines for the AER implementation, and then you compile technical and electrical data and some for the conductors, what kind of conductors is being utilized, and the insulation and so on, and the SAG data, anything that would basically impact the rating of the line, and also the geographic location. So geographic data is very important as well. Is this line on top of at a mountain? Is it like in a hilly area? Is it close to like a desert? The temperature can vary, so you need to have that locational and geographic location information as well. And then you will set up some calculation procedures, meaning that, so which standards are we going to use? Is there's like IEEE 738 standard, and also some IEC standards as well, that could be utilized to calculate the ratings of the lines. And then of course you would say, so this is more like the real-time data. So how do I forecast, right? So you'll see some later on, some more like, characteristics of these technologies that you can actually forecast the rating for next 2 hours, 12 hours, 24 hours, 48 hours, and so on. So by knowing the procedure, by knowing the data that you have for the line, the weather, you can actually, using some AI algorithms, you can forecast the weather, you can forecast the wind, and that way you would you'll be able to come up with some forecast data for the transmission line. So that's what's happening at FERC level. I haven't seen any sort of like major any orders really on DLR. I think AAR is the first step. There's going to be some time for the deployment of AAR, and see how each ISO is actually implementing it. And then the next step, we'll see what happens. The lessons that we learned from AAR implementation, I think, is going to help with deploying DLR as well. But today I'll talk about some of the benefits of actually moving from AAR to DLR. Anyway, so there are 4 different types of line capacity. I kind of briefly introduced them. So number 1 is like static line rating. It really doesn't change, right? So you pick the worst, you choose the worst day of the year. Worst day is the hottest day with low wind, right? And then you calculate the rating for that particular day and say that, yep, this is going to be the rating of my transmission line for the whole year. And the fact is, like, because you can't you can't predict when that day is going to occur. Is it going to be August 5th or August 10th or whatever, July? Then just to be conservative and make sure the system remains safe and reliable, it would just say, okay, so because I cannot basically in real time and forecast, I cannot predict what's happening in the grid. So I would just go with that conservative approach and just pick that one worst day. The other approach is like, well, I can pick the worst day per season. So as I said in my example, like, in Massachusetts, you would pick like 50 degrees Fahrenheit for like wintertime and then 100 degrees summertime as like the max temperature, and just go with that. So that way I know that, in the wintertime, by considering 50 degrees, then I'm allowing higher capacity compared to like 100 degrees to be utilized in wintertime. So seasonal rating is of course like better than static, but again, you're basically considering picking like one worst day for the whole season. And here is we go with like summer and winter only. And I'm not saying this is the only way of doing it. There, like, many regional practices can vary. Ambient adjusted rating considers, of course, like the weather temperature, the ambient temperature. So that way, basically, you are, calculating the line ratings based on the ambient temperature. You're not just considering a fixed rating. You don't pick the worst day. You basically say, yep, I'll just, whatever the temperature is for today and forecast and so on, I would consider that in my AAR calculations. And that way you gain more capacity because you're not being conservative anymore in terms of the temperature. And last but not least is dynamic line rating. So this is the solution that considers both temperature, ambient temperature, and wind. So high wind, of course, it's like more cooling, right? So utilize, we're not going to spend time on, the equations and so on, where those equations come from. But generally in the dynamic line rating calculations, there's like a wind input and then ambient temperature, and then of course like the line characteristics and so on. But wind plays a really important role, actually one of the key factors in determining the line rating. So knowing the wind and considering the impact on DLR, you would actually gain more capacity by applying dynamic line rating compared to ambient adjusted rating. Generally, if there's the reason that I'm talking about DLR, of course, like there are other solutions as well. So if there's like a thermal line overload, DLR is really not the only solution. You can, reconductor it. It's going to take probably 2 to 3 years if you don't have to do anything on the tower. It's just reconducting the cable. Of course, you're going to have extended outages. The cost is probably $500,000 per mile. These are all just estimates. And it would gain probably 34%, around like 30-35% gaining capacity based on existing, cable industry, cable available, cable types. Rebuild, basically building new transmission lines, can take 3 to 5 years, maybe longer. I've heard 7. There's like a lot of permitting issues that you need to deal with. Some extended outages, of course, needed. The cost can be pretty high. And last but not least in this list is dynamic line rating. So you have about like a year timeline to implement, maybe less, with the existing grid solutions are evolving. They're like the easier way of installing technologies. And I'll actually explain that the installations in are not just what you see on the screen. There are many manufacturers have developed their own way of installing the sensors. Some are like tower based, some are tower mounted, some are ground mount, or some the one that you see in this picture is like the sensor is mounted on the cable. So there's a lot of I would say evolutionary work being done to make sure that the implementation time is reduced so that we can easily deploy these technologies. Most of the DLR, almost all the DLR technologies that I am aware of require no outages, which is great. As we're adding more electric vehicles to the grid, we're adding more offshore wind, more solar, the loading configuration, the profile of the system is changing. You're not going to be able to, take outages easily anymore. In some ISOs, actually, that the request to take an outage takes about like 6 to 9 months. Going with no outage solutions is becoming more and more important, where you don't have to deal with those extended outages anymore. So this kind of summarizes different options and why we think dynamic line rating is a good solution to be considered as a tool in the toolbox. I've never said that dynamic line rating is the only solution. Sometimes, yes, you do have to reconductor the line. Sometimes, yes, you have to build transmission lines, but by utilizing dynamic line rating and utilizing that excess capacity that this technology shows that that capacity exists and is not being utilized, I think we can reduce the number of line reconductoring projects and also building transmission lines, which is exactly what the goal is, to keep our grid infrastructure upgrade affordable to our customers. As I said, there are like 3 different types of sensor installations. We have sorry, just give me one second. Okay. So we have like ground-based solutions, LiDAR-based solutions, and vibration-based solutions. The ground-based solution, of course, is I think all 3 are kind of self-explanatory. Ground-based is the sensor is located on the ground. The LiDAR-based, some manufacturers actually installing the sensor on the tower. And then through LiDAR, they have a full picture of the cable. They look at the sag. They can measure the sag and also measure through the EMF of the transmission cable. They can actually measure the amount of current that is being flown through the wire, plus the temperature and wind can be captured through the weather stations as well. The third solution is vibration based. So these are, you see the picture of the sensor. So the sensor is installed on the cable. As wind blows through the cable, the cable vibrates, right? And then that vibration is sensed by the sensor, and knowing the type of the conductor, measuring the sag, this sensor can actually calculate the amount of wind that is flowing to the conductor. And of course, it's measuring the conductor temperature and ambient temperature as well. So yeah, 3 different types of technologies that are out there. Some examples of my, again, previous work at the utility work. So we actually deployed dynamic line rating at one of our, actually 2 of the transmission lines in the Northeast. The results were very I guess, impressive and promising. That's the better word. What I saw, or what we saw, it was that the DLR actually exceeds the static ratings by like 94 to 97% of the time. So there's like a short period of time that actually DLR went under the static rating, the DLR shows like 31% in line capacity increase in average compared to AAR. So going back to FERC order, where I have the AAR order, and then the point that I made that AAR, I think, is the first step towards implementing this dynamic line ratings. Is like, so you implement AAR, you learn lessons, and then ultimately, you move on to dynamic line ratings. We'll see if that happens, but hopefully will. I know there are some challenges, especially on the planning side, that need to be properly addressed. But by doing that, you would gain, 31% in line capacity. And if you compare the DLR data with static, we do see a 47% in line capacities increase. And so if we're going to implement only AAR on this particular line, of course, these numbers are only applicable to that line that we implemented DLR on, okay? Because if you pick a different line because of the geographic location changes, you'll see slightly different numbers. But that's the range that we're talking about is kind of like maybe plus or minus 5-10%. That's or maybe a little bit higher in terms of the range. Anyway, so if you're going to just do AAR with no DLR, then meaning that you're not going to consider wind in the calculations and the capacity, then you would expect, we saw like close to like 11% increase in line capacity compared to static. So compare 11% with 47%, right? So this data basically tells me that going to DLR would give us this 47, an additional 36% capacity gain. But again, the concerns and challenges related to especially system planning need to be addressed properly before we do that transition. The other feature of the dynamic line rating is actually the forecast aspect. So the forecast feature is extremely important to me. Actually, it's more important than real time because forecast could be utilized in operations for like day ahead operations. The real time dynamic line rating, I would say maybe like it's more applicable to like emergency operations. If like an operator needs to do switching right now, something happened, they need to do some switching to maybe take something out of service and things like that, then you would look at the real-time data. But the forecast is like, system operator is planning for like a day ahead market operation. There are like some line switchings they want to do, and not knowing the ratings of the other lines, the adjacent lines. And knowing the impact can be a challenge. So by utilizing this forecast aspect, they would basically say, yeah, line X, the day ahead rating on this line is Y. So I'm doing my switching. I'm going to make sure that I don't exceed that Y, based on my studies. So that way, you don't just rely on static ratings for your day ahead market. You don't rely on ambient adjusted ratings because you're missing wind. So you would by going with the forecast aspect of DLR, then you would say, yep, I can rely on that. This is for the next day, and I know the wind forecast and so on. So of course, like there's always a safety margin for that we consider for calculations. And by doing that, you would say, yep, for tomorrow, here's the rating, so I can operate my lines. such that I don't exceed that dynamic rating rather than just sticking with the static rating, because the static rating or ambient adjusted rating are going to be lower than the dynamic. So forecast is strongly recommended for day-ahead market operations. The other, I would say, you know, one of the most important benefits of dynamic line rating is that it can actually significantly reduce the number of wind generation curtailments. We had, we meaning, you know, that utility that they used to work for, we had a project or like, I would say, you know, some wind turbines in the New York State, and the power of these wind turbines being transferred to the grid through a 115 kV line, and that line, you know, the rating of that line, if you stick with, you know, the static rating, where you know, sometimes during the day or the week being like violated, meaning that the actual power flow through the line was like exceeding that rating. And the wind turbine needed to be curtailed a lot. So basically the goal was to install the dynamic line rating to see, you know, what the actual rating of that line is, if are we being too conservative in terms of calculating the ratings, and the answer was yes. You know, like the data showed that, you know, you can significantly reduce the number of curtailments for the wind generation, because the line rating and wind kind of correlate and work and you know, and benefiting each other. So when the wind blows, you know, wind turbines are spinning, and the temperature is cooler because of the wind. So the temperature is cooler, then the line rating is higher. So that means, you know, there are the times that actually the wind turbine is spinning, then you have more capacity in the system. So it kind of works well if you look at it from the line rating perspective. So this is an example where we actually saw that, yes, you know, we've been, you know, too conservative. The line, you know, the ratings can actually be much higher during the time that the wind is blowing. This curve that you see on the screen, I took this from a NYSERDA report in New York. This kind of shows that the cut-in speed for wind generation is 3.5 meter per second. Of course, like can vary based on the generator type, but around 3.5 meter per second, that's the wind speed that, you know, you would see the turbines start to spin. So if I want to consider my pilot results with just 3.5 meter per second and above wind speed, then that gives me about like 60% in line capacity increase for static ratings. So this data is telling me that if I have wind turbine near this line, then if I see wind turbine spinning, that means in average I'm having 60% in line capacity increase, and that's a great capacity increase. That's a lot of capacity that could be utilized to transmit that wind power without worrying about, you know, reconductoring the line. So of course, you know, as I said, in order to calculate the rating of the line, there are many factors that you need to consider: ambient temperature, solar radiation, wind. Wind is the key factor. Okay, the impact of that, like, you know, on the line rating compared to ambient temperature, solar radiation is a lot higher. So that's why, you know, when you go from ambient adjusted rating, where you're only looking at it with the ambient temperature, you go into DLR, where both ambient temperature and wind speed is considered in like calculating the line capacity. Then you see like a big change in DLR compared to AAR, because wind is one of the the key factor. So in this particular example, even like the angle that the wind is blowing to the line, if that changes from 45 degrees to like the angle to like 90 degrees, you see like, you know, the capacity goes from 35% to 44%. So you see like just 9% increase in just the angle right, of that the wind blows to the line. The point I'm trying to make is, if AAR is good. It's much better than, of course, static and seasonal. But you see that, when you consider wind in the equations and the DLR calculation, then you would see like a major capacity gain. How do you implement this, right? So what's the ultimate goal? Of course, so we don't want to just randomly pick some lines and install sensors on them and see what happens. Number one, you need to do some weather measurements. All right. And I'm sorry, before going to this, the way this works is that each utility that is interested in deploying dynamic line ratings would basically say, yep, here is the KMZ file of my transmission line X. In that KMZ file, all the structural information are there. So where's the tower located? What's the length of the span, and so on? All the physical aspect and geographic location of the line. The dynamic line rating solution providers would basically take that. They would calculate the rating of each span, and based on, again, the location of each span, and they would pick maybe like a few, like one or two, troublemaking spans, or we call it critical spans. So these are the spans that have the minimum rating, okay, amongst the other spans. And the reason that we do span by span is like, the geographic location, the angular shift in the span can have an impact on the dynamic line rating calculations. All lines are not just straight, so of course they shift in angle. Anyway, so by identifying those critical spans, you would only install the DLR sensors on those spans, because those are the ones that are limiting the rating of the entire line. Assuming that the line rating is the only issue, you don't have other limiting elements like breakers and so on. So back to this, we would do the weather measurements either through, one vendor is doing like through the vibrations. Some other vendors actually they bring that data from weather stations. We also, you need to do the line measurements as well. So what kind of loading is on that line, the voltage, frequency, and so on. And then you would use the IEEE standards algorithms to calculate the real-time ratings. There are also ways to calculate the forecast ratings as well from IEEE. But in the end, the goal is to actually integrate all of this to the EMS, or transmission management system, or TMS operations. All right. So by all the ultimate goals, like in the operations center, they will basically saying, yep, I have a screen. I know the ratings of all these lines that I have the DLR sensors on, so I want to do switching here, and that data that are given through DLR gives me the confidence that yes, there won't be any overloads, there won't be any issues, or there will be, and here are the actions that need to be taken. So TMS operations actually, and integration to transmission management system or energy management system is very important, and most utilities are actually interested in solutions that provide this in the package. One of the utilities, there are many utilities in the state that are actually deploying this. So I'm not gonna name all, but one that is very ahead of the game is PPNL, and PPNL have fully deployed the solution and with integration to the energy management system. There are other utilities as well. Again, this is not the only one, and basically there've been working with PJM to make sure that the integration to the PJM operations is also seamless. They're actually currently expanding, in the process of actually expanding the current work that they have done so far. Their anticipation is to save $23 million of annual savings in congestion costs. So there are some states to deal with like some congestion on their network, right? If the cause of that congestion, if the reason for that congestion is the line rating, PP&L is expecting that by utilizing DLR technologies, they can save close to like $23 million in annual savings. They actually published some articles on PJM website as well. So if you're interested, feel free to let me know, and after the call, and I'll send you those articles. All right, I have one more slide. We're done with DLR. I kind of gave you that big perspective on what the DLR is and different ratings like ambient adjusted ratings, static and seasonal. So, and again, there's a lot to be done on that DLR aspect. There are a lot of concerns that need to be addressed as well. We're not there yet. We're not done with DLR, and we don't consider DLR as like the greatest solution yet. It's a tool in the toolbox, and it will work for some locations. Again, as of now, and in the future, we may see, and we will see some great evolutions in that aspect. The other projects that I want to quickly mention that is kind of under this GETS, our grid enhancing technologies category or umbrella is the power flow controller device. Power flow controller, the way it works is, well, let me give you a little bit of background. In the past, utilities had literally no control over the magnitude of the power flow in their transmission lines, right? So they would just dispatch generation, turn on, off, generation in different locations, and then it would measure the power would flow through the transmission network based on the equivalent of an impedance of each branch, right? So there was literally no control over that, and that's not a good thing, right? So in many states in the U.S., like we are experiencing high penetration of renewables, like solar, and so for like a few hours during the day, that solar generation may be at its peak, which is basically which may be violating some of the thermal ratings of the transmission network. Do you want to upgrade the whole transmission line because of few hours of excess power that solar is pushing through those cables? Well, maybe not. If there's enough, if there are enough, or like there are some adjacent transmission lines that do have the capacity, why don't we just push the capacity to those lines and make sure that our lines still remain under the ratings all the time? So this is exactly what Power Flow Controller is doing. It's basically managing the amount of the power flow through the transmission lines. It works. I know we're kind of running out of time, but it works in like two different modes. One is inductive, the other one is capacitive. Generally, transmission lines are inductive. So X component or inductive component is much larger compared to resistive, and even like compared to the distribution as well. So by adding another inductor to the grid, you're basically increasing the impedance, the equivalent impedance of the transmission line, and that if the impedance goes up, the current goes down. And then, but if you have this power flow control operate in a capacitive mode, then capacitive impedance plus the the inductive impedance, the overall the equivalent impedance is going to be less. So that means if the impedance goes down, then the current is going to go up. So that way the power flow is going to increase. And this is just an example of what like kind of like a sample test that we did on that device. We switched, basically the device was in an inductive mode. So the impedance was high, the current was low, power flow was low. and then we switched it from inductive to capacitive. And you see, like, because the impedance went low, the current went up, and suddenly we see like this increase in the amount of the magnitude of the line current. So this way we're able to actually control the power flow, right? And monitor it, control it, make sure that our lines never get overload, and manage that properly. If there's enough capacity on the adjacent line, let's push the power through that instead of upgrading the existing line. So that's pretty much it. I have, so yeah, if you have any questions, feel free to contact me.
Thank you.
We have time for questions, right?
Yeah, thank you very much, Babak. I think we may have like 3 minutes. Maybe we can extend a little more because we have a few questions. Let's see if we can go maybe quickly through them. But
Sure.
anyway, thank you very much. Very interesting presentation. Let me go with the first one. I'll go in order with from the chat box. So from Larissa Afolabi, what does the reconductor solution consist for thermal overload? And why is there no outages in the case of DLRs?
Yeah, so DLR, so reconductoring is basically you're taking the conductor down and then you put maybe like a thicker wire there, and you need an outage to do that, right? You take the conductor down and put a new one there. You're not touching the towers. You can use the same infrastructure, but the wires need to be replaced. For the dynamic line rating, these solutions are like, as I said, let me go to, so ground-based solution, the sensor is installed on the ground. It's basically looking at the wire. The tower base is kind of similar, but it's installed on the tower. So it's using the LiDAR technology to look at the full span of the wire. The other solution is basically the sensor that is clamped on the wire and while the system is live. So there's no need to actually de-energize the system. All three solutions provide that capability.
All right, thank you very much. Now another question from Arturo Núñez. Have you used distributed acoustic sensing or distributed temperature sensing for DLRs? I'm not sure if you're familiar with those techniques.
Distributed temperature sensing.
Distributed temperature sensing and distributed acoustic sensing.
I'm not familiar with that.
Okay, maybe Arturo can reach you out after this
Please.
This webinar. Another one from Arturo as well. Do you see the same increases in line rating regardless of the type of DLR used? I think you already answered that one. Or is it one type more accurate than the others?
Yeah, that's a question that I can probably provide you more information offline. Some data that has been captured on accuracy. There's really, each solution has some benefits over the others. I think maybe if you just shoot me an email, I do have some documents that can provide more information on, if you're concerned about, say, like wind forecast or temperature and so on, or accuracy of the AI algorithms that are currently being used. I can provide you more information on that. We have actually there's also some tests that were done to measure that accuracy. So I'll share that information as well.
Perfect. Maybe we can get well, maybe Arturo has another question, but probably he can also ask you that one through email. I'm gonna jump to the next one and probably just maybe an extra one after this one. So from Navin Shenoy, is a static line rating SLR typically equally to 100% of the conductor rated ampacity, or is a percentage of the rated?
The static line rating is like what? So the test that we did is one of the vendors. So here, for example, I'm showing that the dynamic line rating was actually 47% above static in that particular line. We have generally you would see something around like 25% to like 50%, of course, depending on the location of the line. Not all lines are the same. But yes, the static rating is pretty low compared to the other types of the ratings, because you're being too conservative in terms of the considering the reference temperature for your calculations.
Good, sounds good. And maybe this is a question, a follow-up question from me. It may be also depending on the utility or the transmission line operator, and depending on the standards, right, that they use internally.
Absolutely. Some utilities have different practices, right? I share that 50 degrees Fahrenheit wintertime, 100 degrees Fahrenheit for summertime for one of the Northeast utilities. But that can change, of course, regional by region.
Great. That sounds very good. I'm gonna ask just another question because we're running out of time. A quick one. I think this is also interesting from Eng Hosing. Can DLR help planners in predictive maintenance?
Projected maintenance.
Predictive maintenance.
Oh, predictive maintenance. So like asset maintenance is something that I was not planning to touch on this, but I do have a lot of information on that. So I definitely, if you shoot me an email, I'll share that information. But really briefly touching, yes, currently the dynamic line rating manufacturers are heavily working on the line health aspect as well. So they're trying to make sure that their package, their solution includes just also not only the ratings of the line, but also it gives you the health information of the line as well. So yes, the sensors can give you that line health information, so that you can kind of you would know how many years of line life is left. Is like another 20 years, 30 years, what's that the lifespan of the line, so you can properly manage the either reconductoring the line or building new lines, or whatever practice you would have to address that concern. So the answer is yes. The line health information is part of this, and again, contact me later. I'll send you more information on that. From transmission planning perspective, I also want to mention this, that here I'm saying DLR exceeds the static ratings for like 94 to 97% of the time. We have seen some transmission lines that actually DLR exceeds static 100% of the time. So DLR is always above static. That means the static was too conservative. So if that's the case, and you have like enough worth of maybe a year of data, you may feel comfortable to actually raise your static to the minimum DLR. That's basically the worst day of the year. So with that being said, the benefit of using DLR in planning, or so far one aspect of DLR that is currently being considered in planning is actually adjustment of the static ratings whenever or wherever it makes sense.
Okay, that sounds interesting and good. Thank you very much for answering all these questions, Babak. I think we ran out of time. For everyone else, please reach to Babak on his email that he's sharing right now. Also, thank you very much for joining to this webinar. Thank you, Mega, also for for to organize this amazing amazing time and book this time, and also reach Babak to provide this presentation. And please stay tuned for future Secret US NGN webinars, and I hope to see you all soon. Thank you.
Thanks, Andres. Take care.
Thank you, Babak. Thank you, Andres. Always a pleasure, Babak.
You're welcome. Thank you. Take care, Megan.
Take care, Babak.
Thanks. Bye.